61A Q&A right before midterm 2. So here we are. We're going to talk about fall 2016 question 7, which is kind of like count partitions from lecture. So maybe we'll talk about count partitions and we'll talk about this problem. But let's read the problem and see what we have to deal with. And then we can review how to structure these what are called tree recursion problems. Now there's no trees. Instead, it's the kind of the computational process that evolves from running the code that creates some tree-like structure. Tree recursion is about when you make multiple recursive calls within the body of some function. Okay, so this says implement sums, which takes two positive integers n and k. It returns a list of lists containing all the ways that a list of k positive integers can sum to n. Results can appear in any order. So for example, if we call sums on 4, that's what we're summing to. And we have to use exactly two numbers to get there. And they all have to be positive. Then there's nothing that includes a 4, only stuff less than 4. So we have 3 plus 1 and 2 plus 2 and 1 plus 3. That's the story here. Here we see that if something, then we get to a base case. Otherwise, we're building up the list. So y is an empty list. We'll return y eventually. And y.extend just takes some other list and puts all of its elements into y. So we're just going to kind of like build that up as we go. I think, you know, with any recursive problem, the first thing to look for is how can you decompose it into a first decision and then a recursive call that does the rest of the work. So looking at this example, I think one thing you could do is have your first decision be what's the first number in the list. So we're going to come up with all these different lists, but what's the first number in the list? And then you can decide what are the rest of the numbers in the list.
Steve,
and we'll have to ask ourselves, like, does the rest of the numbers in the list involve some recursive call or not? Yeah, sorry, honey.
Sorry. So Steve, look also at the second example, sums 5, 3, and notice that there are 3 examples with a 1 in the first position. Yeah, 1, 3, 1, 1, 2, 2, 1, 1, 3. Now look after the 1, the 3, 1, the 2, 2, and the 1, 3, and now look up. That's exactly what that is. Yeah. So that tells you, that's a good indication that you're going to do something recursive. You're going to put the 1 in the first position and then just solve using only 2 numbers summing up to 5 minus 1, which is 4. Yeah, which is basically the recursive call from above.
Wow, thank you.
Great. So now we've kind of discovered the recursive structure. It's pick the first number and then make a recursive call to fill in the rest of the numbers. And yeah, if you pick 3, there's only one way to do it. But if you pick 2, then there's 2 ways to do it, 2, 1, or 1, 2. And then if you pick 1, then there's these 3 ways to do it. So that should give us some indication about what the recursive call looks like. If I'm building up a list of 3 numbers, then my recursive call is about filling in the other 2. So we'll kind of subtract 1 from k. And what do these other 2 have to sum up to? Well, whatever the total is minus the first number. That's the kind of rest of the recursive structure here. So now that we kind of know what we're after, we have to figure out how to write it. This for x in something, I think, is an opportunity to iterate over the first number possible values. So that to me looks like a range where the lowest value is 1. And the highest value, I'm kind of assuming here that there's more than one number we're going to add up. And so we can't go all the way to n, because then like we'd have some zeros in there and they're not allowed, right? We have to have positive numbers. In fact, you can actually calculate what's the biggest first number you can have based on n and k. I think the biggest first number you have is when all the rest of them are 1. So to get there, you'd start with n, and then you'd subtract out all those 1s. But you're allowed to have this number. And remember, ranges go up to, but not including the last one. So we get a +1 in there. So when you have a complicated expression like this, it's always good to look at an example. What would happen if n was 5 and k were 3? Well, we get 5 minus 3 is 2 plus 1. That doesn't look right at all. Oh, because after this, there aren't k numbers. There's k minus 1 numbers. So I think we really need like a +2 in there. Okay, let's see if this does the right thing. So we do 5 minus k gives us 2, but we really want to go up to 3. And this expression gives us 4, which is good.
These off by ones, by the way, are killer.
Right, off by ones are killer, but the way to deal with them is just look at examples. I think is almost always the case. So examples won't tell you the exact expression. You have to kind of know what you're after. We're kind of trying to make space for all those ones. But then, like, have you done it exactly in the right way? Well, then you check an example.
By the way, John, would it have hurt if we just went to n? Wouldn't it have just fallen out eventually?
Great question. So what if we go to n? I think we'd have to decide what to do in the base case.
Yeah.
We don't really have room here for a base case that says I have an incompatible n and k value, like a negative n or a k that's 0. Yeah, I guess that's something to worry about.
Yeah, okay.
But if we were writing this totally from scratch, like there's lots of ways you could do it. Okay, so then what happens? We're making a recursive call to sums. We kind of talked about what this would look like is probably there's n minus x value here. We've put x as the first element. And then how many more numbers are we going to have in this list? Well, k minus 1. So this got us to, if x is 3, then our recursive call is going to be summing up to 2. 1 plus 1 is 2. And then we have to think about what this returns. So this is going to, for example, in this one, if we make a recursive call with x equal to 1, we'll get one of these values back, because we'd call sums for 2. And when you're given one of these values back and you want to create this value, you have to write some code that goes from here to here. This thing, the result of the recursive call, is called s. And this thing is the result of whatever expression I put in here. So then I can think about how do I build 1 to 2 from 2 would be something like put x in a list and then add that to the values that are there before. That's how you build a longer list from an existing list. Okay, so what happens? I guess the simplest case would be, I think it would be okay to stop when k is 1 or when k is 0. But, you know, k is 1, I think, is a little bit more intuitive here. So what happens when k equals 1? Then I think there's exactly one way to do it. We're supposed to return a list of lists. So our result should look something like this. We knew that by just reading the problem description. But in this case, there's only one way to build a sum of n using just one number, and that's to put n in the sum. Great question. So this kind of list of x plus s, is that a common trend, and when does it show up? Here's when it shows up, is when you want to build a long list, one element at a time. Then, you know, there's two ways to do that, really. You could be appending things onto the end, or you could be adding things onto the front. Which one do you want? Well, this addition operator makes a new list, which is quite nice when you're doing recursion. Recursion gets very complicated when you start changing lists in the middle of it. So if you start like appending to something, then that usually causes more problems than you want. So addition is nice because it will create new lists every time. You won't have to worry about accidentally changing s as you go. And anytime you're building up a long list, one element at a time, basically like you have most of it and you're adding one more thing on, then you'll see this pattern. And this is the way to have the right kinds of values on both sides of the plus. So if you have a list over here, you need a list over here too. If X is a number, then you have to make a list out of it before you can add.
Noah's asking, I'm going to work up through the chat, the comments in reverse order. Noah's asking, how would this return the empty list as in the second doc test?
Oh, good point.
Yeah.
This says, what happens if you want to list all the sums from 2 to 3? Okay, so if we hit the empty list, this is not true, right?
Yeah.
We'll start with an empty list.
Oh,
we'll go through an empty range, and we'll end up with an empty list. I will say, like, really quickly, that I think you would get the same answer if you had that as your base case. But you do need to like have a base case where you're returning a list with some lists in it. Otherwise, you'll run into trouble. Questions like this are out of scope for this midterm. You can ignore them. We covered this a little bit in the optional efficiency lecture. In the past, this has not been optional, but this semester it is. So if you see anything with like how fast does something run, and you see like thetas or O's and mathematical expressions, we just didn't cover that in discussion and lab. There was a lecture, but it was optional, won't be on the test. But don't worry that your education is being compromised. This will be covered a lot in 61B when you take it, so you don't have to worry about it now.
You have 3.5 years to understand big theta and big O.
Lemon XV. A lemon copy is a perfect replica of a nested lists box and pointer structure. If an environment diagram were drawn, the two should be entirely separate but identical. So they don't share any objects, but they look the same. XV is a list that contains only ints and other lists. The function lemon generates a lemon copy of the given list XV. The isInstance function takes in a value and a type to determine whether the value is a given type, which is something we have seen. So if I have a y and I call lemon copy on y and assign that to lemon y, I'm supposed to get the same picture. But what's interesting is that it might be the case that objects are repeated in here. And so there could be like arbitrary interesting structures there. So here's some examples. If I start with x is 200, 300, and then append x, I end up with a structure that looks like this. Then I have y equals xx, so I have a structure that looks like this. And here's the call to lemon on y, which gives this structure. And here's a bunch of checks to make sure that they don't share any objects, but have the same structure. Interesting. This looks a little tricky. So we're given xy. There's a helper function that's called on xy. I imagine this will be recursive as we kind of traverse the structure there. There's this list lemon lookup, and you notice it's outside of the helper, which means every call to helper is going to have access to this same list. And the name lemon lookup gives me a hint that maybe this is about figuring out whether I've rebuilt this piece of structure already or not. So like everything that's in here, I have to make a new one of somewhere here, but I don't want to do it twice. I don't want to like recreate this chunk twice. I just want one copy of it. So that might be what lookup is all about. Okay. If something returns something, we'll pause there. But my guess is when you get to a number, it's probably time to just return that number. You don't have to worry about whether two numbers are the same or different. There's really only one 5, and that's really not an issue. So it's only for mutable values like lists that you have to think a lot about whether you're creating a new one or not. Okay, so here we iterate for old new in the value that we're dealing with. Old new is a funny name, isn't it? Okay, we're making a new XV. We're gonna append pair into this lemon lookup list, which keeps track of for my XV. Here's the new XV. We're gonna go through for every element in there and do something. I think this is probably where we make sure that we don't make 2 copies of something, and then we'll return the new XV. So let's see if we can make some progress. If something, return old new 1. I'm not sure why we would do that. Oh, I think this is about going through the things we've already built. For old new in lemon lookup, if old new 0 is XV, then we just return old new 1. So what's in here? This is pairs of something in the original structure and new version of that thing. Okay, I think that's what's going on here. So if I've seen XV before, then I just want to return what I constructed. Now I get to the point where I've never seen it before. I therefore have to build something new. I'm going to make sure that I remember what I built, and then I'm going to go through for every element in XV. I'm going to new XV.append the result of copying that. And if it's the case that I get to an integer, then I think I can just return that. Okay, let me see if this worked, and then we'll talk about it. Well, looks pretty good. So I think the like interesting recursive part is here. So let's just make sure that's okay. This says, and like without that, if we forgot all of this stuff and just said, if I hit a number, then I return that number. Otherwise, I make a new list. I go through every element in the old list. That element might be another list with lists in it, or it might be a number. I don't know what it is, but I know I need to copy it. So I call helper, which basically is the copier, and I append a kind of copy of that thing to this new list that I'm creating, and then I return that new list. So that's really the core of making a deep copy of a list that contains other lists, which contains other lists. And the only thing we've added here is to make sure that if I've copied something once, I don't copy it again. And so that's what this is recording when I've made a copy, I want to store it. And then before I make a copy of something, I check and make sure I haven't seen it before. A good question. So where is like, is XV in lemon lookup? It's actually this whole loop. It goes through each pair of something in the original structure and the new version of that thing in lemon lookup, checks to see if XV, the thing that I'm supposed to copy, is the something in the original structure that I've seen before. And if so, then return the new version of that thing. Okay, we're taking a look at lab 9, question 5, generators generator. And here's what it looks like. Write the generator function make generators generator, which takes a 0 argument generator function g and returns a generator that yields generators. My goodness.
I stopped saying generator.
It was a little scary when I highlighted the word generator. It showed up so many times. It doesn't just stop here. It's like down there too. Okay, so for each element yielded by the generator object returned by calling g, a new generator object is yielded that will generate entries 1 through e, yielded by the generator returned by g. So g is the input. So basically, like if g goes 1, 2, 3, then, or I guess g goes 0, 3, 6, 9, then we're getting generators that go 0 and then stop, and then 0, 3 and then stop, and then 0, 3, 6 and then stop, and then 0, 3, 6, 9 and then stop. Oh, and we got a nice short template here. So we'll take a little work. Let's see if we can make some progress. So here's we make one of these. And what do I mean by one of these? One of the generators that goes for a while, but not all the way up. And we get as an argument some I, which I think is good. This is going to like tell us how far we get to go. Now, what's interesting is that G might go forever. So the nice way you might think about this, which is like get all the values in G and then start slicing it, isn't going to work. Because here's a, oh no, this doesn't necessarily go forever. This stops. But maybe G could go forever. So anyway, that's the thing about generators is sometimes you don't want to like get all the values that are in them because there could be a lot. So you kind of want to process them incrementally if you can. So at some point we have to get the contents of G. A typical way to do that would be, is G something we call? Oh, on N and M. So we make generators on this thing, which takes no arguments. So we have to be able to call this, but I guess we know that it takes no arguments. At some point, we're going to call G and get all the values that are in it. And so let's call that an X. I kind of feel like we need to keep track of this. Like, here's everything I've seen. And then for each element that I've seen, I need to yield a new generator. Oh, good question. So what is for X and G? This says for a generator function, get all the values that it yields and bind X to each one in order. That's kind of the right way to interpret that. So G
will it, like,
yields some stuff. Go ahead.
Like, will it like because I think when we learn generators, it was like it goes and then it stops after like each yield statement. So does this like implicitly yield and then would it like start over once it got to the end, or just stop?
A good question. This will never start over. This will only go through all the yields in G once. And what this says is go until G yields, bind X to whatever G yielded, and then do this stuff. And then after this is done, go let G keep running again until it yields again. X is now bound to the next thing it yields, and do this stuff. We need to pass in something. It's not clear to me why I need this I yet. But we'll think about it. So we're supposed to yield a generator that goes through all the values in here, which is a for loop for all the X in scene. I'm not sure why there's an if. What a strange template. Okay, I thought this was just going to go I thought it was just going to go like that. And this is the len of scene. I wonder if this just works. Where are we? Yeah, that works. Okay, so now we could try to figure out why there's this other template and what it's supposed to do. I guess yeah. Another way to write this might have been if I equals 0, just yield scene 0. Otherwise, yield from gen I minus 1. That probably works too. Oh, no, that didn't work at all. Oh, this needs to first yield scene I. Oh, that didn't work at all either. Maybe it's like that. Oh, now I got them backwards. Phew. Okay, well, there's another way to do it. But neither of these ways fit the template. For whatever reason. I guess the easiest way to fit the template would have been to say,
Put a comment there, John.
if false, nothing here.
This is cheating.
And then yield the CNI, and then yeah, print. I know, and then nothing here either. Oh, what have I done?
Right. Oh, you didn't do the recursive call on gen, I think, right?
Well, this was supposed to be my boring version where it just kind of went through
Right.
the elements. Oh, this is supposed to be
Jay.
CJ. Sorry. Anyway, sorry, I'm a little lost on the template as well, I'm afraid to say. But it seems like the logic is a little bit simpler. Maybe whoever was writing this problem wasn't thinking of creating a list of the values that you've seen so far, and maybe there's some other mechanism to kind of track that implicitly, but I don't see what it is. Yeah, good question. So in like a real program, there is a slight speed advantage to not creating new objects. So in that case, like if you're going to build a big long list, one element at a time, then appending is better than just using plus sign and making a new list each time. We don't worry so much about efficiency in this course. That's more of a 61B thing. So that means that you can kind of get the same result just by adding lists together, and that's fine too. Sure. So the question is about how you might reverse a linked list. So let's just say we have a linked list of numbers. I don't know how exactly they did it in the lab orientation, but we can talk about one way to do it. So like originally you have that. How is it that you would reverse it? No, it's not supposed to be an arrow, but you get the idea. This is supposed to be the end of the list. Okay, so one way to reverse it is just to like keep the same link structure that you have, but just change the values. So, you know, you could find a way to swap the 3 and the 1 or something like that. But I think that's probably not what they were after. Instead, I think what they were after was change the link structure. So I don't know how to get a second color, but just pretend that things are disappearing as we go. So basically change the list structure so that this goes here and this goes here and this doesn't go anywhere. This is the end. That would be a way to reverse the list, but you'd actually have to end up returning this thing over here. So, you know, this is gone and this is gone. And this thing over here is the result. All right, so we can try to write some code that does that. We'll see how far we get.
The trick here, as John is setting up, is linked lists are incredibly fragile. So if you don't hold on to, as you start to rewire things, you have to be very careful to hold on to the pieces, because as you start to break links, things can separate. So the trick here is always going to be to make sure you're holding on the pieces as you rewire.
So if we get a linked list with one element in it, then I think reversing it is pretty straightforward. Otherwise, we assume that we have at least two elements. What are we going to do? We're going to reverse everything else in it, I think would be a good way to do it. So reverse of rest is the reverse of s.rest, which should have like recursively fixed up everything except for yeah, this guy isn't really part of it. Right now, you know, s.rest's last element would be empty because it would end there, but you don't want it to end there. You want it to include this thing as well. So, so you could fix those last two links. Reverse of rest.rest equals s. This thing is s. And you'd want to change s.rest to be link.empty. But you want to return the reversed thing. What is the reversed thing? This doesn't look right. Let's get some names. I'm going to do a little more annotating. That's s. That's s.rest. This thing is rev of rest. Oh, I use text editor. So I do think we probably need to keep track of this kind of stuff. So this is like the original rest was s.rest. That's this thing. So now we have a new name for that as well. Now we go through and do some reversing. So now we have a name for this. It's really the original rest's rest that we want to change to be s. The original s hasn't changed. Its rest should be link.empty, and then we should probably return the reverse of rest. So if I have a linked list, let's make it extra long. And I reverse it. Oh, something worked. Oh, except we didn't really reverse it in place. We just built the reversed thing by changing all the arrows. The question is, do you really need this or not? I think the answer is probably no. You probably could have just called it s.rest here as well. But, you know, I thought it was a little bit easier to think about it the other way. Yeah, okay, so it still works.